This session is being recorded, so please turn the video off during the presentation session, and then during the discussion session, we can turn the video back on. So with that, let me start. As I mentioned, we'll be looking at the rate-dependent aging resulting from fast charging of lithium-ion cells. Very quick introduction on lithium-ion batteries. I think most of you are familiar, but just in case if you're new to this, in the case of lithium-ion batteries, you have, so the cathode material during the starting point has lithium loaded in it, and then the very first charging cycle, the lithium moves into the anode. This is typically called the formation cycle. So that's how the lithium-ion batteries, the fundamental principle works. And the electrolyte, there's a separator that's typically polymeric with some ceramic material added to it for structural stability. And then typically aqueous-free electrolyte is being used because of the lithium being water sensitive. So the electrolyte that's being used is organic electrolyte. The reason lithium-ion batteries have started becoming very popular is because of the energy density. So both volumetric energy density, which is given by the watt-hour per liter, as well as the gravimetric energy density, which is watt-hour per kilogram, is much higher in the case of lithium-ion when compared with nickel metal hydride or nickel cad or lead acid battery. And as you can imagine, be it the consumer electronics or automotive vehicles, the lighter, the smaller, the better, right? So the smaller, the better when you go to higher volumetric energy density, lighter for the electric vehicles for sure. So as a result, this has started becoming popular. Now, when you look at electric vehicles, you want to be able to fill it up faster, right? The refueling, people are used to refueling with gasoline. So what's happening now is people are depending more and more on fast charging. And what does this do to the actual life of the lithium-ion cells? This is what this group at Oregon National Lab did, led by Daniel Abraham team. And this is the paper that we'll be going through today. What's happening in the world as the electricity cost keeps coming down, more and more fast charging is becoming economically cheaper as well as logistically better than the slow charging. So this chart shows the electricity price, dollar per kilowatt hour, versus the gasoline price, and at which point it is cheaper to drive electric vehicle with fast charging. As you can see, US is right here. Each of these lines are different countries. And as you can imagine, as you can see here, as the electricity cost keeps coming down with the more and more solar and wind penetrating and the cost of those going down, this is becoming the norm rather than this side being the norm. So more and more fast charging is being used from an economical point of view as well. What does this do to the actual lithium-ion batteries? This can accelerate aging due to multiple reasons. One factor is the internal increase. As we all know, when we do the fast charging, our current is very high. As the internal heating is rates to the I square R, it's proportional to the square of the current, it increases the internal heating and the temperature rises, and this leads to less life of the cell by accelerating the mechanism, the aging mechanism. And what are those aging mechanisms? It can be an internal impedance rise, which is due to what's called SEI, the solid electrolyte interface. This interface is formed on the anode of the lithium-ion batteries, which is the graphite. You form this, the very first cycle, you form this electrolyte solid electrolyte interface, which adds impedance to the cell. That's one reason. The other reason is the electrolyte reaction with the lithium that's plated during the charging, and this can lead to gaseous evolution, which blocks the anode. That will also rise to an impedance increase. And the third mechanism is when you're doing this high rate charging, fast insertion of lithium back and forth, this leads to the strain in the cathode, the oxide material, and that leads to the cracking, which disconnects the cathode material and leads to an electronic conduction issue within the cathode, which also increases the impedance. So these are the three mechanisms by which the impedance can rise due to high rate charging. In addition to this, there's also an increase in the actual polarization, which is the electrochemical potential of the anode, leading to lithium plating. So the lithium plating, what will happen is once you plate the lithium, instead of intercalating the lithium into graphite, you don't have the lithium available to be extracted back for the discharge. So as a result, your capacity is impacted. Not only that, the lithium can react with electrolyte and gaseous products, as we discussed earlier in the impedance case. But this also, in addition to the impedance, can block the electrode surface, which in turn increases the polarization of the anode. As you can see, there's a cascading effect. And then we can, that's what it's covered here. And the other thing that leads to is the lithium plating can lead to a dendrite formation of lithium, poking through the separator and then shorting the cell. This can also be impacting the safety of the cell. So these are the impact of the lithium plating. And again, the non-uniform plating can lead to local lithium plating. So it doesn't have to be the entire anode that's plated with lithium. Even the local lithium can lead to these regions here, these reactions. As we can see, one can lead to the other, and then lead to a vicious cycle, and thus a rollover failure or an exponential failure rather than a linear failure. So when you look at literature, when this group looked at the literature, they saw lots of different attributions. I think there are different cathodes that are being looked at in NMC, nickel, manganese, cobalt, LCO, all of these aspects are looked into. And based on this chemistry of the cathode that's being used, based on the actual test, there are different attributions to this fast charging failure mode. The loss of the lithium plus ion inventory for charging and discharging, the electrode inactivation, which we touched on, permanent charge losses in the anode and cathode. Essentially, the cathode and anode doesn't have the capacity to accept or intercalate enough lithium into their material. The impedance rises in some cases. In some cases, they did not see that. And then the SEI, cathode cracking and gassing that we touched upon. Because of the fact that it's such a system-specific and test-specific, direct transference to system operating condition is challenging, and this is the challenge that the team took over, and they wanted to come up with a way to impact system design conditions based on what they find. So what did they look at? They looked at the anode as graphite and the cathode as NCM 523, which is the ratio of nickel, cobalt, and manganese, 523. Impact of charging from 1C to 8C. I think people familiar with batteries will be aware of what these 1C and 8C refer to. It's essentially, let's say your capacity is 3.1 amp hours or 3000 milliamp hours. 1C is 3000 milliamp of charging in 1 hour. So you'll charge in 1 hour. If it's 8C, you will multiply the current 8 times, and then your charging current will be lower because it's 3000 over 8 now. So that's the reference here, 1C to 8C. and then the accelerated aging tests at different SOCs, which is the state of charge, how much you charge up to understand the impedance rise behavior. Okay, here is the test profile that they followed. The voltage initial formation cycles were at very low charge, C over 10 and C over 25, two of these cycles, and one C over 25. That's the initial cycles. And then the aging cycle is with XC, where the X ranged from 1, 2, 4, 6, and 8. That's this rise here. And then to the specific state of charge. So it ranged from all the way from 30% to 80%. They took the state of charge and then discharged at CO5, held it at 3 volts until the current dropped to C over 100. So that has been the whole time. So C over 5 until 3 volts, and then once 3 volt is reached, until the current decreased to C over 100, and then started the charging cycle again. As part of these cycles, every 2 charge cycle, to determine the impedance, they did a high pulse like this to determine the impedance, and then a slow charge cycle every 20 charges to determine what is the capacity that's left in the total cell. That's the C over 25 up to 4.1 volt. The test end condition. So what did they call as the test end? There were 3 conditions they used. When one of these conditions are met, they call the test to be complete. The area specific impedance of the full cell when it reached 40 ohm centimeter square, which corresponded to a 400 hour of potential static hold at 4.39 volts. So, and this turns out to be about 75% increase from the initial area specific impedance. When that's reached, they called it done. Or if the cell voltage exceeded 4.8 volts during the constant current charge, that was called the test end condition. And the third condition was 100 partial cycles were completed. These partial cycles essentially meant that you ended at this SOC that you wanted, right? And they also did some calculations later using the total charge as an equivalent 100% SOC, and we'll look at that later in the results. Okay. So based on their earlier studies using reference electrodes, they mapped out what the likelihood of lithium plating. Here is the rate of charging, 1C all the way to 8C, and then the SOC, 100% to 10%. So we looked at the lithium plating. It's very likely, somewhat likely, and not likely with these different colors. As you can see, as you go to high rate and high state of charge, there are lots of very likelihood of plating. But when you're at low rate and a higher SOC, it's fine. That's how they mapped it. This is using the reference electrode. The other thing that they did is, instead of using the voltage to determine the state of charge, they used the actual capacity in milliampere per square centimeter as the state of charge. What this does is it forces the cell voltage to be higher as a function of your cycles. So you're actually accelerating 2 ways. One, you're accelerating by going to that SOC, number 1. Number 2, you're pushing the cathode potential to be high because your cutoff voltage keeps going up with respect to the number of cycles. As a result, there is a double factor influence in the aging condition here. Third, test termination versus SOC and charging rate. You can see here, as you go up, you had these impedance rise very fast, and that led to the end of a test. Whereas if you're at low rate, you're completed the full 100 cycles. Okay. Now let's go to the results. Here are the results of the different charging rates. What's plotted here is the capacity fade. So you started with 100% capacity, and as a function of your partial cycles, how did the capacity fade, and what's the relationship, whether it's linear or nonlinear. And this red line here is a very slow charge. It's a 0.5 C type discharge. This is being used as a reference point to compare how the performance is when you're doing it at high rate. Okay, so 100 cycles at 0.5 C is that red line. So at 1 C, everything looks good, 60% SOC or 100% SOC, it's fairly linear. And at 2C, again, fairly linear, although at a higher slope. But as you go to 4C, at high SOC, you start seeing this nonlinear behavior. This nonlinear behavior is what they attributed as cascading failure or the rollover failure, where when you're looking at this linear region, you cannot predict it to be life here. So for example, at 20 cycles here, sorry, this, when I copied here, the 20 cutoff. So 20 cycles, you cannot differentiate between these here. At least here you can differentiate at the 80% SOC. So it becomes nonlinear. Gets even more nonlinear, as you can expect, when you go to 6C and 8C. Okay. So in addition to the capacity fade, they looked at the impedance rise, as we discussed earlier. So this is the 8C at 30% SOC, 20 and 10. You can see at lower state of charge, it's fairly linear, but as you start, even at 30% SOC, at 8C, it becomes nonlinear rise in impedance. And as you go towards lower charge rate, you're getting at least a little bit more SOC with the, you got up to say 30% and 40, and then 60 and 80 became nonlinear. So this is an interesting chart where if you did this particular chart of the AC impedance, not the AC impedance, sorry, impedance rise is without any voltage limit. But if you did a voltage limit of 4.3 volts, most of the cells fell in a linear pattern. This is what they were commenting on when we looked at this chart of the double impact of the voltage impacting your impedance rise, right? When you cut off this voltage, let's say at, this is the cell voltage cutoff going up at as a function of partial cycles. When this actual cutoff voltage was cut at 4.3 volts, you got this linear performance of impedance rise. There was one outlier that they attributed to some initial structural issue that they had in the cell. But most of them were able to have a linear impedance rise with a voltage cutoff. So cell voltage versus impedance, again, fairly correlated, no surprise here, with 8C, 6C being nonlinear, and then 4C. And as you get lower, 2C and 1C, fairly linear. And then they did another interesting study. They took this impedance curves and they extracted equivalent full cycle. Say, for example, you did it at 40% SOC, and based on the capacity value, if you did 2.5 cycles of that 40% SOC, they considered it as one full 100% SOC cycle. That's what they call it, equivalent full cycle. So when you do the analysis that way, here's the impedance rise with high rate, 8C and 6C. And when you came to 4C, here's the performance. And the 1C and 2C is here. As you can clearly see, there seems to be three regimes and strictly dependent on the actual charge rate and not necessarily where you're cutting off the state of charge. And the key takeaway that they're doing this, which is summarized in the later section, is that the state of charge is actually not preventing you from the impedance rise. Say, for example, as part of your control scheme, if you used state of charge as a way to extend life, doesn't seem to be impacting. Whereas I think the voltage cutoff is a good method to reduce the impedance rise. And the team did an amazing job. And after all these studies, they harvested these electrodes and then built a half cell with lithium as the counter electrode, and then looked at the capacity performance of both the cathode and the anode. And these harvested cells gave an interesting observation. On the cathode side, the capacity that they saw in the cathode was within 1 milliamp hour per square centimeter of the brand new right after formation. This is the right after formation cell, and then there was no difference at all. Whereas on the anode side, there was some loss in capacity, about 40 milliamp hour per square centimeter is what they attributed this capacity to be. So there was some impact on the anode side due to the fast charging. And they also quantified it with the full equivalence cycles, and they attributed this loss as you went higher charge rate, the capacity started coming down. And not only that, even at low charge rates with lots of cycles, there was some impact on the anode capacity. So they also did a plot called dV over dQ. This is similar to, in the electrochemical literature, similar to the cyclic voltammetry, but in a full cell mode, where we are trying to understand the peak of the graphite phase. And between these peaks tells you how much capacity you have. And as you see, as you went from the formation to the 20 cycles to 40 cycles, the capacity keeps going down that you had between these two peaks. So that's another one that they compared it with the half cell study. So the benefit of this dV over dQ study is you can do this in a full cell without harvesting the electrode and doing the control study. So in summary, the capacity faded quasi-linearly or non-linearly with cycle number, and it primarily originated from lithium plus losses to the solid SEI, the solid electrolyte interface. The exception to this was when lithium plating occurred. That can be considered as an additional inventory loss in addition to the SEI. In the experiments with CV over 100, the full cells cathode, as we just saw, remained mostly not impacted with the capacity, but the anode capacity was impacted. But in the case of impedance, it was the cathode side based on their reference electrode studies. They comment on that later. The anode, as we just saw, mostly impacted on all the cycles. The full cells experienced voltages higher than 4.3, and that added an additional impedance rise. And this is, they're attributing this again to the degradation at the oxide surface and of the cathode material of cracking. When they adjusted it to the full cycles, the rate is what is impacted, but not the SOC, the state of charge. Intergranular cracking of the oxide particles is what they're hypothesizing. And the possible connection between the cracking suggests that local non-uniformity is what leads to the aging on the cathode side. So that's the summary, and now it's open for discussion, comments, questions. I can bring up the charts later.
Should I have a question? Looks like the hand.
Yeah, go ahead.
Oh, that's a clap.
Yeah, thank you. Yeah.
I'm kind of this lithium batteries and everything. So one thing which was kind of a question for me was like here you were discussing about the lithium plating.
Yes.
I think it's more specific to 2D materials. Like in our group, they have done a study for lithium sulfur batteries where they have used three-dimensional anode, like vertically aligned carbon nanofibers. So when they say about like lithium intercalation or de-intercalation, they say it's lithium plating always, lithium plating and stripping. So like I was wondering, does it have anything detrimental to the battery, or is that dependent on the material morphology, like 2D or 3D?
Yeah, so good question. So you can think of during the 3D as using a lithium as a lithium anode, right?
Okay.
Where you don't have to worry about intercalation into the electrode. In that case, the 3D material is acting as a substrate, and then you're effectively using the lithium as an anode. Then your capacity is very high.
Okay.
But in traditional lithium-ion batteries, not the 3D batteries, but the 2D batteries, lithium plating leads to negative consequences because now you're not intercalating, the lithium inventory is lost. Number two, the dendrite formation leads to the shorting of the
Okay.
cell, the safety issues. Whereas in the 3D, it doesn't form the dendrite, right? It's all local lithium plating. So it's a nice true north for battery industry to have a lithium as an anode.
Okay.
Yeah.
Thank you.
I had a question.
Yes.
The SEA layer that forms in the formation cycle, looks like, right? And
Correct.
does it continue to form, or is the plating the more the concern? So is SEI the first formation and then it doesn't happen? The mechanism doesn't happen anymore, and then the plating continues to happen. I was just wondering, and in both cases, if you can just hold your anode potential at a lower potential, can you remove the lithium plating, or can you remove that lithium, replate it, or send it back to the cathode?
Yeah, good point. Let me start with the first SEI side. Most of the SEI forms in the first formation cycle, but what happens is, let's say you have the lithium plating, that will form its own SEI. That adds additional SEI. Now, to your second question of the voltage impacting the lithium plating, yes, the anode overpotential is what leads to lithium plating. Now, is it reversible? Turns out to be yes. Yes, there is if you do a slow discharge and charge cycle, they call it the healing cycle. In fact, they took one of the 4C cells and they did that, and then they called it the post-healing capacity as well.
Gotcha.
So it is possible to do that. But if you end up in other mechanisms of safety, then of course other issues happen.
Oh, right. If the lithium dendrite forms, it's a different.
Correct. Yeah.
So what the start of the slides that you showed that they were holding that potential at 3 volts until the current goes to 100 milliamps or something. So that
over 100, yeah.
And what was that done for? Just to kind of assume that all the discharge was done, or all the discharge was complete? Is that the reason why they did that?
Correct. To make sure that you are starting your initial starting point is close to 0 SOC, so that your partial cycle is accurate from cycle to cycle. Gotcha. You didn't want, because of the impact of the voltage, you don't want that impacting your cycle length. Yeah.
But then all the SOC they were showing that they were cycling to 30% to 40% from 100%, right? That's how I understood.
To charging. So
they're charging from 40 to 100.
No. Charging from close to 0 to 40% or 50%. It's a charging cycle.
Only
That's
charging.
the fast charging.
Okay. All right. Okay.
Yeah.
So saying the SOC does not, where you stop, as long as you don't go above a certain potential, it doesn't cause a problem on the cathode.
Yeah, the great takeaway is the state of charge is not impacting your impedance rise. It's the voltage, cell voltage, that impacts. And between their reference electrode study and these studies, they are hypothesizing that it's the cathode impedance rise. And by controlling the voltage, you can control the impedance rise on the cathode.
Okay. And if they were to Pareto this problem,
yes,
it looks like the capacity fade on the cathode is a non-issue completely, except the impedance rise, which is what you're referring to, right? With the,
correct.
So if they were to Pareto the impedance rise versus all the lithium problems on the anode, which is the more important one to solve?
So based on this study, I would say my takeaway is that impedance rise is more impacting than the anode side lithium plating impact. And what needs to be done, I think this is where my review of what could have been done is to do the impedance of the harvested cells as well. That way, you could have actually determined that it's the cathode impedance and not the anode impedance. They did the capacity, but they didn't do the impedance of the harvested cell. So that's my, if I were a reviewer of this paper, that's what I would have asked for that.
Excellent point.
Yeah.
Yeah, because then you would have known that how much is the contribution from cathode versus anode.
Exactly.
Like the capacity fade was 0, no fade,
correct.
All on anode.
Correct.
Is the problem when you rapidly charge, is the problem statement due to impedance? If so,
where is the impedance
dominating or anode dominating?
Correct. Yeah.
Very good. Thank you.
Yeah.
It's a very good paper. Yeah, this test and the results, this can be used to develop protocols on how to charge the batteries.
Correct.
Yeah.
I think I like the comprehensive nature of the paper and the connection to the applied. I'm more product and implementation oriented, and I like that approach of connecting the fundamentals all the way to the applied nature. That I liked. It's a very good study from that point of view.
It is not necessary that we have to use a constant, we can use a CC charge, but we need not use a constant rate all the way from 0 to 100%. So based on their study, maybe 10% at a higher rate and another 20% at a slower rate. So that should decrease the effect of aging.
You're buying time. Things are happening, right? Because SOC, as long as, but if you combine that with the voltage control, yes, I agree, right? If you strictly base it on the SOC, then I think it's going to be a problem.
Yeah, so if you plot that as a cumulative amp hours, I'm assuming it will all show the same problem, right? So if you plot degradation as a function of cumulative charge amp hours, then they all should fall on top of each other, I would think. If it is all lithium on the anode problem, right?
Okay.
The impedance is kept the same as long as the charge voltage is maintained, so that you've eliminated or at least controlled the impedance, then your cumulative amp hours should show the same trend.
Yeah, which in this case, they did maintain let the voltage ride up so that they are not impacted by the impedance. But what you're not taking into, or they did a comment on it, is there is an additional mechanism of that high voltage on the cathode impacting further impedance, right? So as a result, I think it will be worth plotting that.
Yeah, it'll be because they plot the equivalent cycles.
Correct.
Which instead of that, so then they show, those 3 bands.
Correct.
You plot amp hours, cumulative amp hours. Would they all lie on top of each other?
No, I don't think so. I think that's what you're asking for is what they did using the cumulative, equivalent full cycles.
Yeah. Yeah, I have to think more about it.
Yeah, but it's worth plotting.
Yeah.
So when we used to do literature, I used to do the plot on my own plot from the data, and yeah, maybe you can present it next week, Mani.
Yes, I will try that.
Great. Yeah. Comments, questions?
I did have one more comment. Sorry, go ahead, somebody else.
Yeah.
Yeah, I was just about to make a comment and maybe a question also, Chuck. Thanks, by the way, for doing this.
Yeah.
And the comment actually is around the applications. So if you start looking at some of the OEMs and the recent announcements, whether it's Tesla, GM, all of these OEMs actually are moving towards having vehicles which can go for 1 million miles plus. And at the same time, fast charging, whether it's with Tesla network or other fast charge service providers like EVgo, Electrify America, those things are becoming more and more clearer. And then like more and more adoption of those things are happening. So that's where industry is going. And it's kind of interesting to like hear you present this. And then where are these OEMs going with their products? I'm just wondering actually if the impact on the battery life will be substantial because of fast charging. I'm just curious, by the way, how might OEMs pencil that needle actually, saying that we can have vehicles which can go for 1 million miles plus, knowing that there will be impact on battery life with fast charging? How can they reconcile this situation?
Yeah, I think it's based on the actual chemistry of the cathode, assuming that their hypothesis, this team's hypothesis is correct, that it's the cracking of the cathode particles leading to impedance rise. Let's say the team developing this will be developing on a similar study on those cathodes to see how the impedance rise is happening. And if it is, then in their protocol, charging protocol, they'll have to limit the voltage and then appropriately control the charging rate. So they may have a mixed, so instead of, similar to what Sabri commented, instead of mixed charging rate based on SOC, it can be mixed charging rate based on the actual cell voltage. Up to a certain voltage, do this. But once you reach the cell voltage, start ramping down on the charge rate.
Mm-hmm.
That could be a pathway.
Okay.
So Chuck, and I think even today, they have in the battery system, they do limit the maximum. They measure every cell, and they will limit the charge rate or to what resistance they charge based on a maximum cell, right?
Got it.
So even one cell goes up, they would limit that charge, and that's all you get from a charge. Mm-hmm. But I think I like this idea, which is go high rate charge until maybe some SOC for life standpoint, which is because we've been blind to that so far. It's all based on one singular point, right? Now, if you do that, maybe you avoid and can accumulate less damage or break these cathode granularity or the structure over the time, at a lower rate than what we typically do with just maintaining one voltage peak, possibly. That's actually a good idea. Yeah. But even, I have a general question, even with all this, even if there's a chemistry that can accept charge 0 to 80 or 10 to 80% in 20 minutes, 10 minutes, mm-hmm. If you imagine the kilowatts in a car or a passenger vehicle or a delivery truck, you need 100 kilowatt, 200 kilowatt power, and you have to dump that in 10 minutes. That's like half a megawatt, close to half a megawatt to a 1 megawatt substation for every car or truck. That's like, I don't know how you put that infrastructure. You know, I mean, I am assuming you need a supercapacitor and slowly charge that, but then your next car comes in line in like 3 minutes. So how do you support this infrastructure? I mean, that's why I like fuel cells in that sense. I mean, I'm biased, obviously. So even if there's a chemistry one day, how can I have an infrastructure that is meaningful to charge it at a rapid pace? You know, that just is daunting. So there are, like Tesla, I think, they've come up with, maybe you go to a steward shop, equivalent shop like mobile gas station, and you would buy one of those aluminum water batteries or air battery, and then replace it and use it as a range extender concept. And then once you go to a particular place, you may have 2 hours to charge. Maybe that may be the transient, you know, evolution in this, until both technologies are ready to be fully commercialized. But it's interesting. Even if chemistry is out there today, I don't think battery, you know, immediate rapid charging can be allowed from an infrastructure standpoint. That seems daunting to me.
I think, can I comment, Chuck?
Sure, please go ahead.
So I think Mani, you're absolutely right, actually. And there have been a number of studies, particularly at NREL, which have come out and showed that. So today, if you look at this, the penetration of EVs in the US nationally is about 1%. Studies show that even if when the EV penetration goes from 1 to 10%, and in a neighborhood, in a suburb with 100 houses, with that 10% penetration, even if one person is doing level 2 charging, even not fast DC charging, which is not coordinated, it impacts the life of substation.
Wow.
And I think if not just one, but so either penetration of EV goes up, or more people actually are doing charging, which is uncoordinated, whether it's level 2 or fast DC, the impact on electrical infrastructure will be massive, which is why a number of energy utilities from SCE to PG&E, even like Con Ed in the Northeast, they are trialing a number of these programs, how to manage the energy infrastructure properly, given this wave is coming. So I think the pain point is real. I actually, if I heard you correctly, you said Tesla had something around range extender as aluminum can?
Yeah, they have patents on it. I don't know if they are thinking about it yet.
I see.
They have patents on it, but that may be just to cover their, you know, full scope of what may happen or what may evolve over time.
Yeah.
Because I think, you know, today, I think there are batteries which can go to 80% range of charge or depth of discharge, I should say, within 20 minutes, right, Chuck? I think there are chemistries out there which do that, but I don't know the life. The life is impacted every time you do that. But even if you accept that chemistry, like to your point, you know, first, even to get to that level of 10 minutes or 20 minutes of charge, to have an infrastructure in one gas station, if you were to count the number of dispensers there are today, and then you have to replicate, that's 10, so I need 10 of them, that's 10 times 1 megawatt, 10 megawatts worth of power. That's just a complete station for every mobile gas station, right? That's a lot of transmission that we don't have today, I don't think.
Yeah, maybe you can sell fuel cells for generating power.
So I think the hybrid makes sense. I don't think fuel cell alone is the answer, or battery is the answer. I think hybrid.
It's a portfolio.
Yes,
we need to have a portfolio solution.
Right.
Right. Other comments? So the other critical thing I was looking at is they could have, if possible, done full spectrum AC impedance to look at some of the time constants that could have helped the cathode particle impedance versus SEI impedance. Maybe. I don't know. I don't know enough about lithium-ion battery AC impedance behavior, but it's possible to separate the time constants.
I agree. By the way, how do they harvest their electrodes separately? Is it easy enough to do it?
They just said harvested, right? Yeah.
I don't know how to, fundamentally, I was thinking about how do you do it for fuel cells? It's a really hard problem.
Correct.
Unless the coating is stuck on one side, and I don't know how. That's a very nice study.
Yeah. Unlike fuel cells, the membrane is not bonded, right? The separator is not bonded.
True.
So
I think the electrodes peel off maybe.
Correct. Yeah. It's very different from that point.
Right. And then that's where the reference electrode always helps you, because you can always learn that same thing in situ.
Correct.
In a cell. But I didn't understand the reference electrode chart. I didn't understand what they were measuring to suggest their regimes there. I was not very sure about it.
Yeah, so they did a very small wire of copper and lithium plated inside the separator, and that's how they used it as a reference.
Yeah, but they were looking at potential on anode and potential on cathode. To
understand the lithium plating potential.
Got it.
Specifically, and also cell voltage versus the cathode voltage, cathode potential.
Yeah.
Okay. Any other comments? If not, I will share the screen again. So next week, I've identified a paper. Okay, so this is the topic next week. So recycling of gold using anodic electrochemical deposition from molten salt electrolyte. So we're covering the entire range of electrochemistry here. So will be good. And again, as I mentioned last week, please, if you'd like to lead, send a note to info@vetrilabs.com. Thank you for joining us. I'll stop the recording now.